to the Fundamentals of Electricity course. In this course, we'll cover the basics in electrical understanding that can be applied to circuits used every day in transmission diagnosis. My name is Lance Wiggins. I'll be your host. It's a great day to fix transmissions, so let's get started. For electricity to flow, we need to provide a conductive path from negative to positive. This path is called a circuit. And while there are several different types of circuits, all of them have a few things in common. In this case, what we're showing to you here is a battery, a fuse, your switch, and your bulb. This would be your component. Your battery supplies voltage to the switch, turn the switch from on to off, supplies voltage to the bulb, and of course you have a negative side of your component. Kirchhoff's law of voltage. Voltage drop in a circuit will increase proportionally with resistance. When added together, the sum of the voltage drops in a circuit will equal the voltage drop of the entire circuit. There will be almost no voltage left over. How do we determine what voltage and resistance and amperage is in a system when we don't have the specifications? The laws of voltage allow us to do this. Just place your finger over any one of the sections, and what's left is a formula for Ohm's law. That defines the characteristic you've covered. So let's take a look at that real quick as we look at this. So this would be what we would consider division, the division line right here. That's the division line. This would be considered the multiplication line. So if we take, as this example, if you cover the E, which is our voltage, you're left with I and R. I is your amperage, R is your resistance. You take your I, multiply that by R, it equals E. So in this case, if we had 0.7 amps, we multiplied that by 20 ohms of resistance, we're roughly going to be using about 14 volts. Conversely, if you cover the I, now we're covering the current, you're left with E over R. So there's where your division line comes in. So in this case, we're going to take the E, which is voltage, we're going to divide that by the resistance, and that'll give us our amperage being used. So in this case, we'll use 14 volts divided by 20 ohm resistance, and it's going to give us our 0.7. Notice we had our 0.7 up here too, so that means our math is good. If you cover the resistance, you're left with E over I. So to calculate the ohms, you just simply divide your voltage, which is your E, divide that by I, which is your amperage, and that'll give you your resistance. So in this case, we're taking 14 volts, divide it by 0.7 amps, and that gives us 20 ohms of resistance. So either way, if you're having trouble with the specifications, this gives you a great way to test that. All right, let's take a look at a series circuit here. We'll cover the basic series circuits in this example that are commonly used in transmission diagnostics. Keep in mind there will be many other types of electrical circuits, such as parallel circuits and parallel series circuits, and many more. The most familiar type of the circuits are series circuits. Would be a simple string of Christmas lights. So in this case, here we have our battery positive connected to a positive lead going up to one light, through a resistor, through a resistor, through a resistor, and back to ground. The DMM, or digital multimeter, is used to measure the basic characteristics of electricity: voltage, resistance, and current. Because the DMM tends to average any changes, it is not the best tool for finding glitches. That would be our oscilloscope, which we would have learned a little bit about that in our tool section of the electricity fundamentals. Intermittent voltages and spikes, you probably won't find them here with the DMM. So it'll give you your frequency measurements, your duty cycles, your min-max recording, relative modes, and display readings for freeze frame. But as far as finding some sort of glitch, your best bet would still be that oscilloscope. Let's take a look at a series circuit here. No matter where we measure the current, it's always the same, which provides the current, which proves that current is indeed consistent throughout the circuit and that it does pass through each component. So in this case, we're going to check our amperage. Notice we have it on amperage. We're going to check our amperage here directly off of this resistor here, which is 0.7 of an amp. We'll test it here, 0.7 of an amp, here 0.7 of an amp, and so on and so forth. Now, as an example, just to put a note here, if there was a glitch in one of these resistors or there was a glitch in the wiring, that number would then change. So if the resistance changed, so let's just say that, you know, this was open, or there was, you know, the resistance in the circuit here was different. We had put a 50 ohm resistor instead of a 20 and a 20, that number would change. In this case, we have a 14.38 volt applied source voltage to the circuit and near 0 volts after the resistance. Almost all of the voltage is being used up by the load in the circuit. There should be no more than 0.1 volts or less of residual voltage left. Using a voltage drop test is the best way to check any ground circuits. The total resistance of the circuit is the sum of each individual load or component, if you will, component's resistance. So in this case here, we're taking resistance number 1. So we're testing here number 1. So we're going up and we're checking the resistance in that solenoid, if you will, or bulb in this case, this load, and it's 6.6. We'll go to resistance number 2 and verify that at 7.7, which gives us a total of 14.3. We already measured voltage before, so the first step to resistance is to prove the principle. There was 14.3 volts applied. A simple voltage check shows 7.6 volts after the resistance. When you're using your multimeter, there's a letter alongside of it. If so, the letter indicates whether you're looking at 3.12 ohms, 3,120 ohms, or 3,120,000 ohms. Now, this is a big deal because when you're testing equipment or testing solenoids, and you get your meter up there, you zero it out, and then you push it together and you look at it and you see OL, or out of limits, right? That may be because you don't have it on the proper setting. Okay, so that could be a real difference in your diagnosis. If there's no letter in front of the ohms, you're reading ohms times 1. So in this case here, when we look at the ohm reading and you see the K and the M, so just the regular ohm reading is approximately 0 to 3,000 or 0 to 1,000. The K would be 1,000 on up, close to millions, and then the M would indicate the mega, or the mega ohms, which would be in the millions. So the difference between the two here is that if you had your mega ohm on and you went to test it, that number would be different. So you want to make sure that you have the correct settings. You should always zero out your leads. There are several things you need to keep in mind when measuring resistance on a circuit or component. Failure to follow these basic procedures can have drastic effects on the results of your measurement. First, isolate the component or circuit. Zero out your leads. Never touch test probes while measuring resistance. Replace worn leads or the batteries inside your test equipment. Use a good quality meter and verify your resistant measurements with an amperage reading when possible. Measuring voltage between 2 points in a circuit or voltage drop. Remember, all of the vehicle's electronics start and end at the battery. Before doing any electric fault code, especially computer communication codes, tests, it can also trigger an anti-theft and radio preset if your battery is bad. Before you do any of that, always go to the battery, verify that you have 12.6 or higher, standing still, not running, good battery voltage. Make sure the clamps are clean. Make sure the voltage on the wires are clean and the cables are clean. Okay, here we're going to perform a voltage drop test. So connect your voltmeter positively to the battery positive post. Then we're going to connect our voltmeter negative terminal to the point closest to the circuit load. On the starter, that'll be the starter power terminal wire. Load the circuit, which means crank the voltage, crank the starter over just as long as you get a stable voltage measurement. Record that voltage shown. If you have 0, then your test is done. We're good to go. If you're recording anything other than 0, so you've got 2 volts or 1.2 or something like that, we're going to go and take a look at step number 5 here, which is move the meter negative lead back to the next connection point on the circuit. In the case of the starter circuit, that'd be the positive cable connector at the starter power terminal. Crank the engine and record the voltage shown on your meter. If voltage still appears on the meter, move the meter negative lead back to the next connection point on the circuit. In the starter circuit, that'd be the battery connector clamp or terminal. Crank the engine and record the voltage shown on your meter. If voltage drops back to 0, the problem is in the positive battery cable between the last 2 points that you checked. So simply, using your negative lead to follow the line back up to the battery will give you a adequate voltage drop test. So in this case, you'd want to replace the cable and recheck the voltage. So this is going to conclude our course on fundamentals of electricity. We want to thank you for participating in our virtual training solutions powered by ATRA. Until next time, let's keep fixing transmissions together.